Hello, and I hope everyone's doing well. This video is the lecture on regression using categorical explanatory variables and all subsets regression, which is a method of variable selection. Let's start by looking at an example, and this comes from some data that was collected from 189 infants in 1996. This data was collected in Massachusetts, and what they were looking at was factors that would be correlated with low birth weight. And so here's a list of some of the variables they collected, and you can see here we have a mix of some numeric variables like age of the mother's weight, and then some categorical variables like race, smoking status, history of hypertension. And down here is just a couple of table statements so we can get an idea of what's in the data. The R code that I supplied to go along with this lecture has table statements for all the variables. I didn't want to put all of that in the handout because that's background information. So let's first just look at a simple linear regression with just one numeric predictor, so we can kind of compare this with what we're going to do next. And so in this regression, they were looking at mother's weight as the explanatory variable, and I see that I actually changed the name of this variable before I send it to you. So now it's called MWT. So that's the predictor, and they're using that to predict the infant's weight. So we have a regular simple linear regression, while pretty low R squared, although the p-value is significant on the coefficient for mother's weight. So the next question is, how can we use some of that other data to improve this variation that's being explained here? So next we're going to look at a multiple regression using both the mother's weight and smoking status. And here's a table of smoking status. That's a categorical variable. We had 115 non-smokers and 74 smokers. Now we can add this into the regression model just like we added variables in for multiple regression in the last lecture. And we can run it, and what we'll get is it will say smoke yes, and that will also have a coefficient, and we can see here that now our adjusted R squared has improved. So how did R put the words yes and no in an equation? So what it did is it created a substitute numeric variable. Really, only numeric variables can go in regression. So if you put a categorical variable in, R is going to say, well, I'm going to change that into a numeric variable. So it's going to take the, in this case, two categories. No is the baseline, and it's doing no first because of these are in alphabetical order. So this is the baseline. Okay, so it's going to give our numeric variable a value of 0 when smoke has the value of no, and a value of 1 if smoke has the value yes. And what this is going to do is produce a regression model with the same slope but different intercepts for each value of smoke. So we'll see how this works on the next page. So this is our regression equation here. We have two variables, x1 and x2. So x1 is our numeric variable of mother's weight. Okay, and x2 is our 0, 1 variable for smoking status. And so our coefficients from the output, okay, so here's our intercept. That goes in here. Here's our coefficient for mother's weight. And here's our coefficient for smoking yes. So recall that x2 equals 0 when smoke has the value no. So if we take a 0 and we plug it in up here for x2, okay, that makes that whole term disappear, and what we're left with is this equation right here. Now, when smoke has the value no, okay, substituting in a 1 here for x2 is just going to make this term right here minus 270.13. And so when we write all that out, and I guess I did a step of simplification, so I filled in the missing step right here. That's just going to be, like I just got done saying, 270.013, and I can combine this with the intercept. So combining those two terms, which is what the step I have right there, gives us this new intercept. And what we have here is two regression lines, and we have two lines with the same slope but different intercepts. So those are going to be two parallel lines, and that coefficient on our 0, 1 variable is going to give us the distance between those two lines, which we'll see by graphing them on the next page. So that distance between those two lines tells us that on the average, the birth weight of infants born to smoking mothers is 270 less, because it's negative, than the birth weight of infants born to non-smoking mothers. Now, to graph the two lines, we're going to have to do a couple steps first before we do the ggplot statement. And the first one is to find our predicted values. And to do that, we're going to take our linear model object, which I called LM smoke, and we're going to feed that as an argument into this predict function. That's going to return a vector of predicted values. And the next step is to take those predicted values and add them to our original data set. So that's our original data set. So I'm creating a new variable here, a new column called pred smoke, and that's taking my predicted values. You don't really need to do that predict LM smoke line separately. Okay, it's folded into this next statement here in step 2. So we're going to make our ggplot, and we're going to start off with just a regular code to do a scatter plot. We're going to map the smoke variable, that's our yes no variable, to color. And so up to here with the geom point geometry, this is just our scatter plot like we've done before with a third categorical variable. So the new part here is in this statement right here, geom line. And notice that geom line has its own aesthetic mapping. And here, so we're taking that pred smoke predicted values that we created in the previous step, and we're mapping those to the y-axis. I've just used the theme black and white because I think it shows up better. And what that geom line statement there does is it gives us a separate line, one for no and one for yes. And you can see that there are two parallel lines and with the different intercepts. So that 0, 1 coding worked out really well for yes, no. But what if we have a categorical variable with 3 categories? So what's going to happen if there's 3 categories is that R is going to create 2 of those dummy variables. So instead of just the 0, 1 variable, there's going to be 2 0, 1 variables. So for category 1, both of those variables will be coded as 0. So this is category 1 is our baseline value. And R is going to automatically put those categories in alphabetic order. So whichever category comes first in alphabetic order is the one that's going to be the baseline. Okay, then for category 2, the first dummy variable is going to get a value of 1, okay? And this will be the difference between the baseline when the value is from category 2, and then for category 3, okay, the dummy variable 1 goes back to being 0, and the second dummy variable is now a 1. So we're going to measure the difference between the baseline and the category 2 predicted values, and the difference between the baseline and the category 3 predicted values. And we don't have to do any of this. R is going to take care of all this automatically for us. And to extend those ideas, for 4 categories, we'll have 3 dummy variables. First category is always the baseline, and then we'll have 1 dummy variable that measures the difference from that baseline for each of the remaining categories. So we can see again how this extends to 5 categories and so on and so forth. So on this next page we have an example of this where now we're going to put race into the model. So black is the baseline category because it comes first in alphabetical order. The coefficient for race other measures the difference between black and the other category. And the coefficient on race white measures the difference between black, the baseline, and white. And we can graph this in exactly the same manner. I don't have that code in this handout, but it is in the R code script that I gave you. The next topic that we're going to look at is related. It's another method for variable selection, because suppose we wanted to do variable selection on this example. Well, the first variable to come out would be race other, but that's a variable that R created for us. So how do we take that out? We can't actually take that out by itself. So this next method is going to help us take a more global look instead of a step-by-step look at variable selection. So all subsets regression, as I just said, is a method for variable selection. And so what it's going to do is, instead of removing the variables one by one in reverse stepwise or backward elimination, we are also called it, it's going to look at all possible combinations of variables to see which one provides the best model for explaining and predicting the response. So how many subsets are there? So each possible variable is either in the model or out of the model. Okay. Now, if there are only 2 predictor variables, there would be 4 possible combinations, because variable 1 would be either in or out, and variable 2 would be either in or out. So our 4 combinations are We could have variables 1 and 2. We could have just variable 1 only, or we could have 2 only, or we could have neither, which would just be just the intercept or a horizontal line. Now, of course, like we would never do all subsets regression if we only had 2 variables. But this is just so we can think about how many combinations there are. So what if we had a third variable on here? So now our possible combinations are 1, 2, and 3, 1 and 2, 1 and 3, 1 only, 2 and 3, 2 only, 1 and 2, and 1, 2, and 3, which would give us 8 possible combinations, coming from 2 times 2 times 2, or 2 to the third for 8 possible combinations. If there are 4 predictor variables, we're going to have 2 times 2 times 2 times 2, or 2 to the fourth. So we can see that the number of possible combinations increases exponentially as the number of predictors increases. So if there are 5 predictor variables, there's 2 to the fifth, or 32 possible combinations. If there are 8 predictor variables, how many possible models are there? So I'll give you a second to work that out. And there are 8 predictor variables. There's 2 to the 8th, or 256 possible models. In general, if there's p predictor variables, there's 2 raised to the p possible models. Okay, so 256 models, that's a lot. That'd be 256 different linear model statements if we wanted to check them all. That would be a lot of linear models. But fortunately, there's an R procedure that will do that for us. It's in the package Leaps, which you'll need to install just once. And then call up the library Leaps, just like we do with ggplot2. And the function is reg subsets, or regression subsets. And you put a formula in this function, just like with a linear model. And the formula you put in is like all the variables, or all the variables you want to potentially include in your model. And just like with a linear model, you're going to say what your data set is. This line, n best equals 1, says 1 best model for each number of predictors. I think I took that out of your script because that's the default. It's not really, that line is not really necessary. And then there's also an argument NV max. The default on this is 8. I put a 9 here just because I wanted to include all the variables. But 8 is a pretty reasonable number, which is probably why that's the default. And you'll need this method equals exhaustive argument also. Okay, so you'll want to put that into some object, like I put it into what I just called reg subsets out. And then I am going to create a summary of that object, which is going to give us a whole lot of stuff. So I want to just focus in on a couple of things that it tells us. one of those is r squared. And so if we want to look at just r squared, we can use this statement right here. So this is taking the, it's giving us like a table here where if there's a 0 in the column, that means the variable is not in the model, or if there's a 1, that means the variable is in the model. Now r squared can only increase when variables are added to the model. So we can see here as the number of variables in the model, which is actually over in this column. This is number of variables in the model. As the number of variables goes up, okay, r squared can only go up. So if we were going to just use r squared as a criterion, we would just always include all the variables. I want to make a note before I leave this page. So when you run this, if you're working along with the script as you're watching this, this runs like incredibly fast. I mean, think about it. It did 256 regressions for you. And it runs in like a second, maybe 2 seconds. Now, as you increase the number of variables, remember, that's going to increase exponentially. So once you start increasing the number of variables, this could take a moment to run. And what also increases the time to run it is how many observations you have. This is a pretty small data set with only 189 rows. If you start getting like thousands or even like millions, hundreds of thousands of observations, then it will start to slow down. So, and you need to kind of pay attention. You don't want to put in like 30 variables here when you have 100,000 observations, or it will take a couple minutes to run. It should still run, but it could take a little bit of time. So as I was saying on the previous page, r squared can only increase as the number of variables increases. So that doesn't make a very good criterion or a very good way to choose a model. And this is why we have adjusted r squared. Okay, adjusted r squared is adjusted, as we looked at the formula previously, it's adjusted by the number of parameters that are in the model. So we can see what's happening here is, when we have only one variable in the model, which looks like the most important one is this UI, uterine irritability. When that's in the model, we start off, that's the first one that goes in, and we add another one. The second one that gets added is race white, and it goes up, and then it goes up for 3 variables, up for 4 variables, up for 5 variables, and then look what happens. It starts to go down, and then it's going down now as we increase. So right in here, this looks like this row here is the best adjusted r squared. And so that would be with the model, with the variables, mother's weight, race white, smoke yes, hypertension yes, uterine irritability. And we still have that issue with like race white is not actually a separate variable that we can take out. If we look at our very next row, we'll see though that race other is the very next variable, and these are pretty close. So we're going to actually be leaving in the race variable. So we can also plot this, because this table, and in fact this was hard to squeeze on with just this many columns. I had to just move some spaces over. if you start having more variables, that can get really big to look at. So there's a plot that kind of makes it a little bit easier to look at, and what we have here is it shows the adjusted r squared on the y-axis, and then each variable along the x-axis, and it shows with the various adjusted r squared values like which variable is in the model. So at that r squared we only have the ui variable, and as we go up you can see what variables get added at every step of the way. And so this black line across right here is all variables in the model, but we can see that's not the best adjusted r squared. Same thing we saw in the table. This is just a graphical representation of the same information that's in the table. So you can look, so right here, this is your best. And then you can read down here which variables are included in that best model. Okay, so we'll also have a lab that goes with this lecture that we'll do in our Zoom class, where you can take a data set and go through these similar kind of steps with a different data set. So I will see you Thursday.